Okay, when we analyze the circuit, there are two domains we can analyze. One is called time domain, and another one is called frequency domain. This frequency domain is because of the impedance depending on the frequency. If you remember previous video, this impedance is J omega C. So this omega is 2 pi f frequency. This angular speed omega, the 2 pi f. So frequency depends this impedance. The capacitance, very high capacitance, f is large, so capacitance value decrease. Very low frequency capacitance value increase. Okay, and inductor, this inductance is J omega L, and this omega is 2 pi f. So this opposite trend, the inductance impedance increase as frequency goes high. So very high frequency the inductance is like very resistive, and when frequency go very low, then this become inductance become very low impedance. Okay, so frequency domain and time domain, we talk about the transient analysis. And so we start with the time domain. For example, we have this kind of circuit. And if it's sine wave, we can simply use this impedance to solve. Now, what is the voltage here? Ex. It's relatively easy. But if this signal is something like a step function, or even gradually goes up, so say 0 to 5 or 3 to 5. So we have to analyze this and use a transient analysis. We have to make a differential equation. Let's say R 1, 2, 3, and in order to solve the differential equation, we have to have an initial condition. Now, initial condition, when it's step up, this is a big change in less than very tiny time element. So we consider this very high frequency. The very high frequency, this capacitance become like a zero impedance. On the other hand, inductance become very high impedance. So the circuit look like this. Oops. So inductance become like an open circuit. Capacitance is like a short circuit, right? So R1, R2, R3. So this Ex is going to be whatever initial voltage, this voltage says E, is going to be E R3 over R1 plus R3. So this is going to be the initial condition. Okay. On the other hand, after it goes steady, the voltage change is become steady, right? So what's happened? The ending condition is going to be the opposite way. Thus, the capacitance look like open circuit because capacitor is charged up and it's become like zero frequency, 1 over 0, infinite impedance. On the other hand, inductance become short circuit. Okay, so you can tell EX is going to be R2 over R1 plus R2 E. Okay, so we can tell when you have a step function, initially the voltage is going to be this, say we call this EX1 and EX2. So it's going to be EX1, then it end up with EX2. Okay, so this transitional transient voltage is going to cause output like that. So you can tell pretty much by using short circuit and open circuit for the impedance. Okay, so this is good for finding initial condition for solving differential equation. Now differential equation, when you have this inductance and capacitance mix, you have I dt and di dt. So it's become second degree differential equation, and the easiest way to solve is Laplace transformation. And this, you will take this course in the math course in the college. Laplace transformation is just like a Fourier transformation. You transform this into Laplace notation and solve it using algebra and convert it back to time domain. So you can get the exact function here for the change of this voltage, and you can complete transient analysis. The problem is when you have a nonlinear element like a transistor, bipolar transistor or MOS transistor, we have to use some approximated model. For example, bipolar transistor, we can use, say, this is IB, and IC, this is a current source, and this connected by beta. And this beta is, of course, is not constant. Beta is a function of temperature, and it's also depend on the operating point. So it's pretty much non-linear. So how do you solve this kind of problem? We can basically we use Kirchhoff's theory, and the Kirchhoff's theory. Let's see. This is the electrical engineering 101, how to analyze circuit. Kirchhoff's method. So when you have a network, whatever, we define the nodes, and there are two ways to make a equation to solve this network. It's the current method is you check every current going to the node, the sum is 0. So you have how many nodes you have? 1, 2, 3. Say this is a linear, the sine wave. The 1, 2, 3, 4, 5, 6, 7. You can make a 7 equation, or loop, voltage loop method. The voltage loop method is total voltage across this loop is 0. Okay, so again, you make a loop, the enough number of loop to satisfy the number of unknown variable. Then either way you can create matrix equation. Basically it's a simultaneous linear equation, and this matrix equation, you solve it, then you get voltage whatever. But this element can be transistor. And how do you handle linear? You use iteration to find the correct operating point and plug in to the Kirchhoffs. So what's happened is the software often used is SPICE. SPICE does all of this by computer program. So if you give the component around interconnection information, component and interconnection, then software create this simultaneous equation, and is solved many times until each nonlinear element becomes, basically using this model. Most transistors also can have a similar model. So using that model, and until this nonlinear operating point is satisfied, it's repeat solving this many times, then find out each element. Now SPICE does this. Say this is V in and this is V out. So for V in, input voltage, output voltage, it can calculate. So it shows the effect of input voltage to the output voltage. It's also calculate time domain for E out. So certain time E in is certain voltage, create this, and next time step create this time step. So each time step it's make a plot, so it tells you the transient characteristic exactly the way you want. Now it's very convenient that you should learn how to use SPICE. It's not that difficult. The difficult part is modeling. What is modeling? Okay, the modeling is the, say, transistor is not just transistor operation. When it comes to time domain, there is a so-called parasitic capacitance between nodes. Okay? And also there is a internal resistance, very small, but internal resistance. So the model is going to have, and also the characteristic of like bipolar transistor beta, and this has with L, with other temperature parameters, for the MOS. This model is precisely handled by SPICE to get the accurate result. And this is beyond the human's paper and pencil calculations. So SPICE is going to handle this, and that's why the circuit, even the 10 circuit element inside the transistor model, there will be another 10 components. So it's going to expand really big. But computer is good at solving a matrix linear simultaneous equation. So it's just keep crunching and get exactly the time domain analysis you want. Input, output analysis, and time domain. Okay? So these parasitic capacitance is on the silicon chip. Any transistor you create have a certain amount of capacitance, and that is the reason why you make a transistor small, the capacitance becomes small, and switching speed, when capacitance big, it's become dull and slow. When you make a transistor small, then capacitance small, the switching becomes sharp and quick. So the gate speed, so-called gate speed, in a digital circuit, transistor size matters. And transistor size becomes small, gate speed increase, and overall IC chip performance increase. Okay, so that's the time domain. Frequency domain, what we have to look at is the whatever the source, if it's nonlinear, for example, step up 3 volt to 5 volt, this kind of wave, this is a function ft is transformed by Fourier transform. So you get the frequency characteristic, frequency and amplitude. And for example, like filter, you can design even without actually executing Fourier transform, because what you know is E output. When frequency, the higher frequency component of this step function, the higher frequency, the capacitor become like a short circuit. So it doesn't generate much, it doesn't contribute to the E output. So what's happened is this is called low pass. The only lower frequency is going to show up here. So what's happened is, for example, input is like this. This is a typical, the sine wave. You use a diode and make it positive power only, and you feed this low pass filter. This low frequency is like this, and the high frequency is going to be here. So the low pass filter is low only pass, then high frequency is going to be disappear. It doesn't contribute to the E out. So after passing a filter, this signal become like that. Okay, so that's the way we get the DC voltage out of AC. So you plug in AC and go through diode, make a positive signal, and go through this filter, we can get pretty much good DC. So you can tell this how it works. And now, for example, this kind of circuit, C and L and R, has the peak impedance, because L goes big when frequency increase, but C goes low when frequency decrease. So impedance here is going to be pretty low, some peak, and like that. Okay, so using this peak, detecting this peak frequency, and knowing this C, we can measure L. So if you have a coil, you attach to it and run this frequency analyzer, and they have frequency analyzer. It does Fourier transform for you and show frequency domain characteristic. And if you run the frequency analyzer, it shows the peak frequency. From this frequency, you can calculate L. Okay? So that's a frequency domain analysis. We're going to do more detail in the following videos. Okay? So if you're interested in this kind of college levels electronics, please subscribe. Let's look at the hand-on electronics. Okay, hand-on electronics. Today, we're going to show you just simple construction of something we talk about. We are applying a square wave, 200 hertz, very low, and duty cycle 50%. Okay, we're applying to what is this is a signal entry, and you have a resistor. Resistor is connected to small capacitor, and small capacitor going back to the ground. So it's just a series of resistor and a capacitor. So what's happened to the voltage across the capacitor? Okay, so if you look at this, duty cycle 50% square wave is the input, and voltage across the capacitor is change by that exponent equation we talk about, and come back, go up, come back. Okay, so this is the exact equation we talked about in a previous video, and we're going to start talking about time factor RC, or R over L, the time constant for this kind of circuit, how to calculate, and we determine the time versus this voltage change. The voltage change time versus voltage change by time. And what is so important? This is like a typical timer IC chip. Use timer IC chip like a 555. It's measure how much voltage accumulated in the capacitor, and it goes to comparator, and when it's reached to the reference voltage, then it's discharge capacitor and start it over again. So that's the way you can control the time of oscillation. So you can create any time kind of oscillation by just the reference voltage and the comparator. Okay, so when you have a reference voltage programmable by microprocessor, like the I/O port is going to give step voltage as a reference, then oscillation speed can be controlled. Okay, so this is the basic there. It's the voltage gradually goes up and come down, but this come down speed depend on this reference voltage. Reference voltage is programmable, and that's the way they make a programmable timer. Okay, we're going to do that very soon. Okay, if you like to learn more about electronics, please subscribe.